right. All right. Good morning, everyone. I hope that all of you was not affected by the flood. You was, no? Yeah? So you spent Saturday carrying around sand sacks? Okay, well, I did. We got water into the garage. Okay, half a meter of. Yeah, you got flood as well.
The basement, but I didn't do anything.
Okay, so you just let the fish go in and. Okay, good. Well, good. Okay, it's gone. So good. Nice. So let's get started. So we should go back to what we were left with during the last lecture, in which we basically discussed conformal transformations. Which is a set of frame transformation extremely useful if you want to simplify your life, and I'm going to give you an example later, or if you want to generate modified gravity theories, okay? You can use both ways according to the application that you are interested in, okay? So that's how the conformal transformations are defined. So we just have a scalar function f, and f is a function of a field, right? And therefore, the field depends on the space-time position in general. Might be a dynamical variable. And you understand that this guy here is not this metric here. What is preserved in this transformation are the angles relative one to each other, right? Because you see this is just a scalar function, so the metric represents the scalar product, okay, which is related to angles, right? And this is just multiplying the scalar product. Okay, so the angles are not affected, only its magnitude. Okay, that's the property of the conformal transformations. Once we have the definition of the conformal transformation, we just can simply use the definition, how this is constructed, to derive the square root of minus g of the metric, which is useful whenever we are computing the actions, because this is defined, this is the element used to keep the volume invariant, the infinitesimal volume invariant. Then, of course, we have the box operator, which is affected as well. And it's kind of easy to understand because in the box operator, you have metric, tensor to which is applied, tensor to which is applied, okay? With the two indices on the same side, and the metric is keeping one over the other, right? Here there is the metric involved, there is this process, and therefore the Christoffel symbols are involved. And therefore you get that the box operator is not the one that you get before the transformation, okay? Then same principle, also for R, again, just applying brute force the definition of your conformal transformation, you get this entry. So you see that the original Ricci scala prior to the transformation is affected by the f to the minus 1 term, let me write it better, and all of these other terms. Okay. This is quite a key point, especially here, because whenever we apply this transformation, if we start with the usual Ricci tensor, we end up by introducing these kinetic terms, okay? So I'm going to show you, this is manifestly kinetic, because this is just, this is W, comma mu, W, comma mu, okay? This is a kinetic term, like you have in the Lagrangian, so that can be identified with a kinetic term. And this one looks a little bit weird, okay, but if you integrate by part, I will sketch it later. I will not do the full derivation because it's just a by part integration. But this guy is going to give you a kinetic term of exactly this fashion, okay? Therefore, all of this guy is a kinetic term whenever you interpret it within a Lagrangian, okay? That's the thing. So we have seen it already during the last, well, the other nice things that I would like to stress, so these are kind of mathematical derivation, is that the electromagnetism, so basically the Maxwell's equations, are conformal invariant. Meaning, whenever you have your electromagnetic field tensor, you apply the conformal transformation with your whatever function f and function of a scalar field, then you get an electromagnetic tensor with a very, 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 very same structure, the very same you started with. Okay? What does it mean? That whenever you use this sort of covariant transformation to electromagnetism, there is no coupling between phi, the field phi, which is the function on which f is based on, and the electromagnetism, and the photons, if you want to think in terms of particles. Okay? So no coupling. And we were thinking about, when we introduced coupled dark energy, where the field, with the interaction term that we introduced, we realized that the field was coupled to matter, but not to radiation. Okay? That would be the case. Coupling of radiation equal to 0. No coupling. Okay? That's what we were left during last lectures. On top of the derivation of our action, once we apply conformal transformations. And we have seen how we can use the conformal transformation to go from the Einstein frame to the Jordan frame. Just recall it briefly. So we have our action, which again contains our invariant volume element. And then we have what? Gravity. Therefore, we have our Ricci scalar. Then we might have a scalar field, which is again a function of g mu nu of our metric, and a scalar field phi. And then we have matter. Therefore, we have the Lagrangian of matter. Again, depending on the metric that we are dealing with, and then just phi, which is the field, the scalar field, describing matter. Okay? Don't think about it in terms of dark energy. This would be dark energy, if you wish. This would be the other scalar field, which represents the matter component. So that's what we did. Then what we did? We went through a conformal transformation. Therefore, we had the omega. We are going to transform this guy. And we are going to use, well, to transform. We are just going to use this construction. Therefore, we are going to substitute we are going to substitute our square root of minus g that we have there with f to the minus 2 of this guy. Square root of minus g. And from here to here, we did nothing. It's a matter of rephrasing. Okay? Because this guy is equal to this guy. We haven't done anything. And then we do the same here, here, and here. Okay? Therefore, what we get? We get our Ricci, which we can re-express using this guy here in terms of the transform Ricci. Therefore, we're going to have f to the minus 1 tilde minus 6 g tilde mu nu w comma nu w comma nu plus 6 box tilde w. Okay? Plus what? Our other two Lagrangians. And we are going to have L phi, but now we want to express this g in terms of g tilde, using, again, that very same expression. F to the minus 1, g tilde mu nu, and then our scalar field phi, and the same for the matter component. Minus 1, g tilde mu nu, and then we have our field, what was the parenthesis squared? So we have this one, and then the squared one. Okay? From here to here, we did nothing, sort of. just a rephrasing using this expression. Okay? Then what we realized, I mean, I'm going to show it later, but we realized the fact that the key concept that you need to remember is that this guy is a kinetic term. And what we can do is to get this kinetic term and put it together with this one. Because this guy is going to have this Lagrangian, if it's you know, just the one of a fluid, we are going to have a term of this kind. Okay, and look through the expression of W, that you can see it here, you see that W comma mu is related to the derivatives of phi comma mu. So you can put them together. If you do that, you end up by finding that this Lagrangian is actually equivalent, not different, it's equivalent to write something like that. -1 R tilde, so this is just this guy here, okay? And then what we have? We have this Lagrangian in which we glue together this kinetic term, and therefore we get a rephrased Lagrangian, total Lagrangian. Phi, G, mu tilde, and then with respect to phi, and we are left with our matter field. Now look, I'm just relabeling this function such that when I call it like that, the f to the -1 belongs to this function. Okay? And such that I can have our tilde written there without this additional factor in front. Okay? So I just did sort of like that. Okay, I relabel lambda to lambda tilde such that this function, which is a function of G mu and mu end of the field phi, just contains also the inverse of the function f. That's what we got. Are these two Lagrangian different? No, they are exactly the same, equal, equal. Same Lagrangian. Same Lagrangian, and what we get, same equation of motion. What's the difference between the two? Okay, look what we have here. Here we have standard gravity, Einstein gravity. Here we have a modified gravity. Okay, you interpret it in this way. It's not really modified gravity because it's still GR. Okay, it's kind of massaged and changed in a way such that we have a term which is not the one that we would have in the Hilbert, Einstein-Hilbert action, which is the one up there. For this reason, this is called the Jordan frame. Whereas this one is called the Einstein frame. From here to here, we just did a frame transformation. We didn't change the physics. It's the very same theory. Yeah?
Just a small question. On the second line, there we have -6 to G mu, and there should be a plus because we moved to minus.
No, there are a few steps involved in the inversion. There is the minus there. I checked. Okay. Okay, so that's what you have to keep in mind. We didn't change physics. Okay, just because this is equal to that, all of this is equal to that, and then these two guys are just equal to this and that. We haven't done anything. Rephrasing. Now, why is this important? Because perhaps, well, there is another thing which is important. So here we could have sort of modified gravity, if we wanted to call it like this. But there is something else that was not present up there. Look at this expression. What do you have here? You have an f of phi. We introduced a coupling between phi, so between the scalar field phi and the matter field. We have an interaction. We have coupled dark energy, or a coupled field in general. So we have interaction between these two fields, as well as we have it here. That's why we have a modified gravity, phi and r. Okay? So here we have a coupling between f, the field phi through f, and the Ricci scalar. And here we have a coupling between the field phi and the matter field, which is coming up here. So the two, you understand now that what happens is that we have gravity that is pulling in one direction, and the coupling that is pulling in the opposite direction, such that we have exactly that. But the same physics is there because the objects and whatever is out there in the universe is behaving in exactly the same way. Yes?
What happened to the metric, like the square root?
I forgot it. Thanks. Okay. Good. So these are the key points. Now, why that thing is a kinetic term? I'll just sketch it very briefly because otherwise it's endless. Well, we have that, well, the standard Lagrangian, so the canonical Lagrangian for a scalar field is 1 minus 1/2 phi comma nu phi comma nu minus v of phi. Okay? Then I just recall the expression that I wrote there for W mu, which was defined as 1/2 f comma mu over f, which is as well f comma phi comma mu over 2f. Okay? From here to here, it comes just because phi is a function of phi. F is a function of phi. Therefore, it's just the chain rule to arrive at this expression. Okay, just chain rule of derivatives. Then what does it mean? Well, we are going to need the covariant derivative of f to the minus 1, which is equal to minus the covariant derivative of f over f to the power of 2, just the inverse of the derivative. Okay. Remember that the covariant derivative obeys Leibniz rules. That's why this is possible and this is happening, which is equal to, just using the definition of f prime, which is coming from this very definition, we can rewrite it as 2f w comma u over f to the power of 2. F and the power of 2 goes away. And then, finally, which is the term that you need to kind of identify, we have as a kinetic term, which is in the end to be this guy here, just again by using the construction that we have at the beginning there, we just make the substitution, and we get f comma phi over 2f to the power of 2 phi comma, I used nu, phi comma nu. Okay, so you see that indeed those two guys, this guy is a kinetic term of the field with just this prefactor. Okay, that's nice to see. Then remember that what we need to do is not to change, what is relevant here is not to change and reshuffle this term, but the integral of this term. Okay, because that's the thing that is going to be relevant for the equation of motion. Therefore, what we need to do is to basically work out our little bit of action. Therefore, we have the omega, the root of minus g. and then tilde, and then we have f minus 1 box operator tilde of w, which is the guy up there, okay? So we integrate this guy by part, so we just, well, remember it's always between two fixed points, A and B, and the action is a function, right? So we are varying phi, and we're searching for the path that minimizes the path between the two extremes that are fixed, okay? So they give you two fixed points, A and B. So we can, therefore, rewrite it as the omega. This is just, I haven't done any, I'm not going to do anything here, just, if you wish, some embellishment to make clear where the integration by part is done. So you see, we have a function times derivative of this, well, actually the divergence of this guy here. Okay, so now we can integrate by part. We are going to get a term which is given by proportion to f to the minus 1, and then this guy here, which is completely irrelevant because this is between a and b, and that's a constant. Gone. Then what we have? Minus the integral of the rest. Integral of the omega square root of minus g, and then w comma mu tilde, the comma mu f to the minus 1. Okay? Now take care, because here in a way we are assuming metric compatibility. Okay? Because you see we have repeated indexes up and down. What does it mean? That I have a term g mu nu, then I would have comma mu nu, and then this other guy mu f to the minus 1. Right? And therefore the function that I would be integrated with will contain this term and this term. Okay? Therefore, this guy here, the function which goes in front of this divergence here, would actually contain a f minus 1 g mu nu term. Okay? And therefore, here we would expect to have the covariant derivative of fg. But then we need to apply the product rule of derivatives. And therefore, we should have a term which is the covariant, which is equal to wait, that's minus 1, f minus 1 covariant derivative of g. But this term is equal to 0. Okay, little subtlety. Okay, good. So we are left with this, and now you see why I was computing this stuff. Because I have this expression that I'm going to plug it here. Therefore, we have this term that contains a w comma mu. W comma mu, which is going together with this one, which is this guy. And this guy is what? The kinetic term of the field. Okay? Therefore, our beloved Lagrangian is going to look like L phi equal to f minus 2. Then we are going to have all the terms that belongs to the original Lagrangian of our field for f to the minus 2 minus 1/2 comma phi nu comma nu minus v phi plus 6, and then we have 2f w comma nu minus 1f comma nu, where this guy is the, this guy is this one, and this one is this one. and the factor of 6 is coming from here. Okay? Then it's just a matter of reshuffling, and you end up by finding this expression, minus 1/2 f to the minus 1, 1 minus 3, f comma phi over f to the power of 2, phi comma mu, minus f to the minus 2, f to the minus 2, v of phi. Okay? That's what we get. And look what's the structure. One kinetic term, one potential term. What happens? We just redefined a potential and a new field phi. Therefore, God, what happens to this board? We can write it as well as that. Mu minus u of phi. This is a canonical potential. A canonical potential. Okay? Let me just, I don't want to get lost into the computations, but I wanted to show you the subtleties that can enter into this computation. So, from here to here, I think it's clear. We did nothing special. What we did was to rephrase all the terms that are involved with respect to this rephrasing of the metric. We changed frame, okay? No change of physics, because from here to here we have unequal. Then what we did is just to get all these terms that now we know to be of a kinetic structure for the field phi, together with the kinetic term that we have in this term, such that we have a redefined Lagrange for one scalar field. We didn't change physics, okay? It looks like we introduced a new degrees of freedom, because we have an f of phi, so it looks like we have an additional field, but actually it's not. That degrees of freedom got swallowed by this Lagrangian. Okay? And the fact that this guy, that this is actually putting these together to give us a canonical potential is coming from this computation. So we just have the canonical potential at the beginning, then just by how this guy is constructed, we arrive at this expression. So you see that this phi term that we see explicitly here, there is the G mu nu, okay? Quintal for one of these two indices is up, like here, is just proportional to the kinetic term of the field. Is a kinetic term of the field. Then the other important bit to remember is that we don't have to look at this guy as a kinetic term. What is relevant is the integral of this guy must contain a kinetic term, which pops up once we do an integration by part. We do an integration by part, and this guy pops up. That we have it here. That contains a W of phi. That multiplies with this guy. That gives us that. And boom, we have our explicit kinetic term for the field. Okay? And this step, remember that we use the metric compatibility. Having that, we just put the original guy, which is here, plus the original term that we didn't touch here, and the guy that only the relevant term that we kept by keeping through the integration by part, we have another term of this sort. They go together with this one, okay? Because these two guys are proportional to phi. And we get a standard kinetic term, okay? Standard kinetic term with a relabeled potential and a relabeled field. Let me write them nicely at the board so that you have it clean. Oops. Therefore, the new Lagrangian, so the relabeled field is going to be phi equal to f to the minus 1/2 square root of 1 minus 3 f prime over f to the power of 2, 1/2, the original field, comma mu. That's the new field. I say new because it's not new, okay? It's just a rephrasing of this guy. This is a fixed function, and this guy is the real field. And the potential U of phi is just defined, so that's just a definition, of f to the minus 2 of phi of v of phi. Again, the new potential. Okay, again, it's not really new. It's rephrased, okay, is relabeled. That's what we get, and it gives you a structure of a canonical field. No new degrees of freedom. Okay, yes? Sorry? Where, sorry? Ah, sorry. Phi is the scalar. Stick, like that. Okay, yes. And you see that basically what we have here is just the square root contains the square root of two terms. You see? And then proportional to phi. The comma here, that's because it's the derivative of that. Okay? So that's what we get. Nice. Now, practical application. R2, as I mentioned. We have two of them. One is to simplify your life. Okay? Why is that? Because, for example, we can start with a modified gravity theory, in which we have a whatever function f of r. We are going to study theories that also have two structures. Plus the Lagrangian of phi, okay, it depends on the metric and on the field phi. Then we have the Lagrangian of the matter that depends on the metric and the matter field phi. And what's the problem with that? Why should we make a conformal transformation to go back from the Jordan frame? You see here we are in the Jordan frame to go to the Einstein frame. What's the problem of remaining in the Jordan frame? That if you want to compute cosmology, all the lambda CDM stuff that you have seen so far are not valid because they are based on general relativity. They are based on something that has a Lagrangian of this sort, not with that. Okay? Therefore, you need to redo cosmology. What is the advantage of that? There is no interaction term. There is no coupling. So this is said. No coupling is nice, because then you can interpret all observations without any problem. So baryons are we are sure that they are not coupled to a scalar field. There is no interaction, and we can interpret spectroscopy and all of that without any trouble. That's good. Now what we could do? We could use a conformal transformation and then just get an action that looks like minus g, and then we have r. I drop the tildes here. You understand that I'm doing a conformal transformation. And we get a term which is R, L of phi, that now contains the conformal metric. Well, let's put the tilde then of our scalar field phi. Then we have our guys with G conformal and phi. What's nice here? Ooh, R. We can use the cosmology that we had together. Cosmology that we already did. So we know. This is nice. But we have an interaction term. And this might be a pain with the photons, with the baryons, because we need to reinterpret the observations basically. So in practice, what's the meaning of this guy? We have a modified gravity, but we have conservation laws for matter. T nu of the matter component is equal to 0. Conservation. We didn't modify matter. So we have a modified gravity, but a non-modified, if you wish, matter component. Whereas here we have the non-modified gravity, so standard gravity, but we have an interaction term. Therefore, we're going to have T mu, again, the same is for the field, but it's going to be different than 0. We're going to have our energy density flux that contains the exchange, that carries the exchange of energy momentum between the field phi and the matter component and the field component. Okay, that's the thing about conformal transformation. Only one last thing about it, because this is one of the two applications, which is to simplify your life. But then there is the other one, which is the one related to the generation of different theories. So, other thing is generate new models of gravity. Because if I write this action, S equal to the integral over the 4-dimensional interval minus square root of G of R plus Lm G and psi. That's one thing. What am I not doing here? There is not the field. There is not an explicit term containing a scalar field. Okay? No. Explicit, actually it's not even present. L of phi. There is not. Okay? And if I write the action S, which is now based not on this metric, but on this metric, that's not the same. I don't get the same equation of motions. I have an additional degree of freedom, which is hidden in the F here. These two guys gives you different equation of motion. Okay? And that's clear because you basically have that your G tilde is equal to f of phi of G, which is G tilde of G of phi. You can write it that way, right? That is to dependencies. When you do you compute you apply the least action principle, right, to find the equation of motion. What do you get? You get a term which is of the sort phi, comma, mu, variation of G, mu. Okay? Just recall the process when you did GR to derive the equation of motion of general relativity. You start with your action. You go for the least action principle, so you just look for the variation of S, which is minimal. For the phi, that gives you the minimal variation. Therefore, this guy is, so the variation equal to 0, therefore the minima. And you get a term of this sort. This is nu. You get a new term. Okay? These are the two things you can do. Simplify your life to move from the Jordan frame to the Einstein frame, or the way around, from the Einstein frame to the Jordan one. Because maybe what you want to do is to simplify your life to do the computations. You get all your derivations, you do all your stuff in this frame such that you can save cosmology. And this is done, for example, in numerical simulations. Okay, in n-body numerical simulations, people are using the standard cosmology, okay, lambda CDM, for example, but then they introduce an interaction term for matter. Okay, such that they don't need to modify entirely their algorithms to compute that are based on lambda CDM cosmology. They just have to do a little modification in the codes, because what you just get is a G that is time dependent. So they have to change one number in an entire gigantic infrastructure, which is the code that you use for n-body simulations. Okay? So in general, doing the math is generally simpler here. But then if you want to compare to observation, you get your package, you transform it into the Jordan frame, and then you can make your direct comparison with the observations. Okay? That's the business. Keep in mind that in general, you cannot always, if you start with one theory, you cannot always have both matter, so dark matter and baryons with a coupling equal to 0. It's not always possible. Sometimes you have mixed frames in which you have conservation of this sort for dark matter, but not for baryon, or the way around. So what you want to do always is to arrive in the situation in which baryons are obeys conservation laws of this sort, because are those that you observe through spectroscopy and all the other means that we have in astronomy. Okay? Mixed frames. And the idea is to do the transformation, that keeps you the one for where you keep the conservation for baryons. Okay? Now, that's all cute and powerful, extremely powerful, but it is just one transformation. Are there others? Oh, yes. There are a lot of other transformations. Sorry if I use this corner, but I don't want to wipe the board every 3 minutes. Other transformation, for example, we can have G mu nu, okay, which would be our transformed matrix, which could be like the one that we have in the standard conformal transformation plus some other term. Phi, comma mu, phi, comma mu, for example. Now, if you do that, you can end up in quite complicated businesses, okay? So they should be tailored if you really, really, really need it. Another one, for example, is G tilde mu nu, F plus phi, comma mu, phi, comma mu, G mu nu. Take care of this one, equal. This is not linear in G mu nu. So this term is linear in the metric, but this term is not linear in the metric because we have an index up and an index down. And this guy is hidden the metric. Therefore, we have a G and G. This is non-linear in G. So take care about this sort of stuff. And another one, just to end up with a few examples, G mu nu is equal to F plus R of G mu nu and G mu nu. Okay, what's the complication of this one? Because this is the Ricci scalar that comes from the Ricci tensor, that comes from the Riemann tensor. They contain double derivatives of the metric. Therefore, you have double derivatives of the matrix times the metric. Okay, that's quite a complicated transformation as well. Okay, they look cute, but they are not that cute either. Okay, and you have the freedom you want. They can very easily escalate in something ugly. Okay, good. So that's the message regarding conformal transformation. That they are, so that's what they are. This is just some facts about the mathematics. Once we apply that, we can move from the Jordan frame to the Einstein frame quite fluently. We can help ourselves in simplifying the mathematical derivations, or to save the code that we already have without the need of writing from scratch new ones. Or we can generate new gravities theory. Just one, perhaps since I'm on that, I can show you what would be. Can we get dark energy from this thing? That's coupled matter with phi, yes. But we have dark energy. The one that we would expect, slow rolling and all of that. Which kind of fluid would we expect? So look, this guy, what would contain? Would contain a kinetic term, right? What would be the potential? 0, right? We would have V equal to 0. So what does correspond to? Well, we have the generation. Once we do our conformal transformation, if we apply a conformal transformation into here, we basically get a kinetic term in addition. So in our Lagrangian, we would have something of this sort, mu phi comma mu, the one that we did before, minus a potential, which is 0. Now let's get the properties of such a fluid. This Lagrangian is describing our fluid. Sorry, it's phi. What would be? Well, we would have we would have like the pressure, which is equal to 1/2 phi comma dot minus V, and then we would have the energy density 1/2 phi dot plus V, remember? But now what? The potential is equal to 0. So pressure and density are equal to that. Okay? What is the equation of state? It's the ratio between the two, which is equal to W to 1. Is it similar to the accelerated expansion that we see nowadays? No. Okay? Therefore, if you want something that looks like dark energy, you need a potential term in your Lagrangian. Just by doing that, you don't have it. Okay? Just as a final touch. Good, so we can stop here for now. We can have a break and resume at 15 past midday, and we will speak about F of R theories. So these are modified theories of gravity.